We could do without the ozone layer. That would make my life a lot easier.
You're listening to The Cosmic Cast.
Hello and welcome to another episode of The Cosmic Cast, brought to you by the Earth and Solar System team at the University of Manchester. I'm your co-host Marissa Lowe, joined by my co-host Tom Harvey.
Hello.
And this week we're doing something a little bit different. We've not got a random guest on from across the world. We're actually talking to some of the PhD students or past PhD students from here in Manchester. So lockdown's obviously been going on for a while now, so quite a few of the PhD students here have actually handed in their thesis. So one of the guests that we spoke to all the way back in October 2019 was Matt Varnam.
Hello.
Hello, Matt. Thank you for joining us, and
Nice to be back.
Belated congratulations for handing in your thesis.
Thank you. Yeah, it's quite a relief.
So as I mentioned, we spoke to you about a year and a half ago now about the work that you did on SO2 monitoring at different volcanoes.
Yeah, that's right.
Yeah, so would you mind recapping for the audience, what was the main questions you were trying to address with your PhD research, and why were you looking at them?
Yeah, so we're very interested in the gas emissions coming out of volcanoes because they tell you quite a lot about what's going on under the surface. Volcano is basically a huge chunk of rock. How can you get an insight into the magma that's deep inside and predict what it's going to do in the future? And so people have found that looking at the amount and composition of the gas that comes out can be very useful for predicting eruptions in certain situations, not all, but in certain volcanoes. It's a very useful way of telling what the volcano is going to do next. And so then I was specifically using some ultraviolet instruments, so kind of a wavelength that gives you sunburns, wavelength of light that gives you sunburns. We use that because sulfur dioxide can absorb that light, and using some cameras that see this ultraviolet light, we can work out how much sulfur dioxide is coming out. And sulfur dioxide is a particularly interesting one because it's the third most abundant gas that comes out of a volcano after carbon dioxide and water. But the carbon dioxide and water are obviously present in very large quantities in the atmosphere. I mean, water in absolutely enormous quantities. You get rain and clouds, and then carbon dioxide in increasing amounts with climate change and the emission of man-made CO2. So we can't really tell. It is quite difficult to tell those gases apart from the background of the atmosphere, whereas sulfur dioxide is basically not at all present in the atmosphere because it quickly gets converted into like sulfuric acid and falls as acid rain.
Yeah. So I know a big part of your research was, I guess it's not as simple a story as you're pointing your UV camera at a volcano, monitoring the SO2, and then just going, yep, that's all fine, that's the values, we can just use this and that's okay. Obviously volcanoes are unpredictable, but you were looking at how difficult it is to actually measure the SO2.
Yeah, exactly. So if you think of a very kind of foggy day, you can only see a few meters in front of you, whereas on a very clear day you could see miles and miles. But there's always there's usually a limit to how far you can see. So if you're standing on top of a mountain, you look across, the horizon's sort of quite hazy and everything gets a little bit washed out. And it turns out that happens even more quickly in the ultraviolet, so you can't see as far. And the issue with that is it then means that rather than looking at SO2 when you're looking through your camera, you've also got light that has not traveled through the plume. So, you know, what the stuff that's supposed to be absorbing it is the light that's come straight through. And then some of the light hasn't come through the plume and is arriving at exactly the same spot. So how do you separate those two things out? It's quite a tricky challenge.
So I guess that brings us quite nicely onto maybe some of the main findings from your PhD work. I think you put this together in a paper actually recently.
Yeah, so all part of kind of quite a hectic period over the last year, getting papers and thesis together. So the main finding of that piece of work was that you can actually use some quite simple models to replicate all the effects that this kind of extra light coming in produces. So previously people had done some quite complicated models of modeling kind of every single interaction of light in the atmosphere, with kind of saying, oh, well, if there's this much gas between the light travels from the sun to your instrument, and it's interacting with kind of, you know, you've got all these atmospheric gases, and it's X probability that this particular photon will interact with the atmosphere, and that's quite a tricky computational problem and takes quite a long time. And then at the other end, you had people who would just say, oh, well, let's try and just look at a different wavelength that's slightly higher up. But that faces challenges in that SO2 is less sensitive there, and also it still doesn't entirely remove the effect, because they're typically looking, it's still in the UV, but doesn't give you a sunburn. So only slightly less energetic.
Yeah. So are those, say, the methods that would be adopted at most volcano monitoring stations already, and maybe the model that you've come up with is easier, or I'm not sure?
They're largely not adopted at, like, none of the methods are used at volcano observatories by and large. The main thing that they try and do is get close to the volcano, which removes the effect completely. Though to varying degrees of success depending on where you are. And, you know, the work of a volcano observatory is very tough. There's lots going on, and so you don't always have people looking into how strong these effects are. And I mean, I think it might be missed at some volcano observatories, that this could be causing sort of a fair underestimate in the amount of SO2 coming out. But I think that's still very much open to debate, and currently there's only a few of us in the volcano world who are looking at the problem and saying, look, guys, we've got to make sure that this isn't happening at a lot of places.
Ah, okay. I guess I'm quite biased because I always hear you guys talking about this, so I always think, oh, this must be like just a general thing that everyone's aware of. But yeah, by the sounds of things, it might just be a bit more widespread problem.
Yeah, I think there's quite a lot of people who are kind of vaguely aware of it, but maybe not entirely sure how to show whether it's happening, and have some idea of how big of an effect it's having. It's generally just done by saying sort of, oh, you know, we're within a kilometre, so it should be fine. But sometimes they're not within a kilometre, and you just still sort of, you say, oh, well, it might be around this percent underestimate. It's very hard to show, especially because it actually depends on the amount of SO2 present as to how bad the effect is.
Yeah.
And a way of kind of understanding that is that if you have a plume of kind of unlimited amounts of SO2, now, you know, completely can't happen, but if it was unlimited amounts of SO2, it blocks all the light. And then if you have some diluting light from kind of that hasn't passed through the plume, that gets kind of bounced into the path of your instrument, it's actually going to look like there's no plume there at all, because all the light is scattered, has been scattered in.
Yeah.
and so you can't see any sort of signatures of SO2 in that at all. So yeah, you would you would be looking at huge amounts of SO2 and see nothing.
Yeah, that's really weird.
Just to get an idea, when you're talking about the difference between like where your instrument is versus a more kind of direct detection, what sort of distance difference is that?
So typically you set up, for normal monitoring, you set up fairly close to the volcano. You try and be underneath it, such that you can sort of scan across the entire thing with a spectrometer. So you have like a rotating head on a kind of box, and then that rotates the telescope that's looking at the plume. But it's very much dependent on kind of where you can get access to and how low down you have to be in order to see the whole plume. So I think it's typically around 2 or 3 kilometers beneath for a lot of these. But then there's also other instruments like SO2 cameras, which is what I work with a lot, where you're more to the side of the volcano, and that can impose more limitations on where you can place your camera, because you can't get too close to it, and if you're too far away, then you've got a big hill in the way of all of the gas that you want to see. So you need like a really good vantage point, and that can be easily be 4 or 5, and I've seen higher than that. But at that point, you're starting to run out of light that's travelled through the plume, actually, which is quite weird. I think so. For my particular example, I was about 5 kilometers away from Messiah volcano, which is a very nice volcano in Nicaragua. Some American did a tightrope walk over the crater at one point.
Wow.
Insane, I know. And then so I was 5 kilometers away, and at that point, half the light that I was looking at had not come from the plume.
Okay. Wow.
Yeah.
Cool. It's a big difference. I guess it is kind of interesting then for you to be contributing to something that might be more used in future, do you think?
I hope so. I think it's an easy way to quantify how much it's happening, and it does provide, like, it can provide corrections as well. There are some limitations in that it doesn't take into account like the ways that light kind of might bounce around inside the plume as well, which is more of an effect when you have like loads and loads of sulfur dioxide coming out. I think the big eruptions, and especially big fissure eruptions. So a good example of that would be Kilauea in 2018, where the entire lava lake drained out of the side of the volcanoes, about 100 kilometers away, and it was just releasing absolutely enormous quantities of sulfur dioxide. Kind of similar in magnitude a country's emission.
Yeah.
So over the span of your PhD, you've obviously done, a massive amount of work. How did you go about organizing that into papers and into a thesis as well? Did the papers go into your thesis, or was it more traditional format?
Yeah, so I did a format that University of Manchester does quite a lot of, which is this paper format. So it's where you get 3-ish, there's some ambiguity on how many it needs to be, but I did 3 papers in it, and you combine those together, and then you add sort of some introductions and methodology, and a very thorough kind of look at what's previously been done in the field, and then that's your thesis, instead of having to write this full long form thesis that other people at other universities might have to do. And I do quite like it as an approach, because it means you get a bit more of a focus on writing papers, which is what you get to share it a lot, because theses don't tend to get read as much, whereas a paper hopefully gets lots of readers. And
so it seems more efficient to just have the papers already ready rather than having to restructure a thesis, which definitely makes it easier for publishing them. And I believe you've published one of the papers from your work, which we'll link in the episode description.
Yeah, so I've actually got two out at the moment. So the first one was, I think actually, Tom, you were asking about sort of how you kind of carve up the work. So the first one was mostly about that kind of all of those scattering and kind of bouncing of light that I was talking about, and a simple model to try and correct for that. That was all that first paper, and it dealt purely with spectrometers rather than the camera that I had out there. So yeah, we've done this huge expedition to Messiah with lots of monitoring pieces of kit, and then I published using just one spectrometer that we took out. Mostly, well, yeah, mostly because it was it's just much easier to kind of visualize what's happening, and I don't want to go into too much detail. Like, it was already getting quite long, as you know, it took me quite a long time to explain here. So that all fitted nicely into one paper. And then the second one was actually expanding it to all the rest of the pieces of kit that we had out there, and actually acted as quite a nice demonstration that all of the stuff that I was talking about wasn't complete rubbish, which is always nice. So kind of the first one's just demonstrating the model, and then the second one's testing it quite nicely. So the way that we tested it is, yeah, we have the camera that's trying to monitor how much gas is coming out from 5 kilometers away, but then we also did what's called a traverse underneath. So we have a car that drives underneath the plume with a spectrometer pointing up. And Messiah is actually very unique. Messiah volcano that we were at, the measurements, is actually very unique because it's very flat, like insanely flat for a volcano. So you have I think the point of the volcano is like 600 meters above sea level, which might sound like, you know, not a huge volcano, but yeah, there's something there. But actually the surrounding land's pretty similar. So the traverse road is where you're kind of driving up and down. It's just like a normal highway, but you're driving at about the same height as the gas is emitted. And so that removes any of the problems.
Yeah.
But it only works at that volcano. And so it's a great test of what we were showing. And, you know, we can see that when we just do things without any of the extra stuff that I've kind of did for that first paper, our camera that's 5 kilometers away is reading about, I think it's about a 1/10 or an 1/8 of the traversing car.
Okay.
So huge discrepancy there. Clearly there is a problem, and then we go in do our correction, and then they line up very well in the amount of gas they're emitting, sort of plus or minus 10%, depending on the exact conditions.
Yeah, well, that must have been a nice relief then. Yeah,
definitely. I mean, when I came back from the field trip, I had no idea what was going on, really.
Okay.
It's just like I've measured it in 2 different ways, and I have got 2 very different numbers. And so it was all about investigating what on earth was going on, and there was a bit of literature about it that I just hadn't come across properly, or hadn't fully understood. And I think it was only when I kind of started seeing it in my own measurements that I started understanding what was going on.
Yeah. Well, I'll put the link to both of those in the episode description, so the listeners can check it out. But yeah, how was it putting together that thesis, putting together all those papers, and then submitting it during lockdown?
I mean, very tough. Like, so the first paper was sort of already together, and I'd submitted it for the first time December 2019. So that's kind of before everything had happened. But during lockdown, I got I got basically a message that I needed to do some very major revisions to that paper. And so that actually took several months. I think this was at the start of the pandemic. I think I got it back sort of April to make these changes, and I was working very slowly then, very slowly. I think for me the hardest thing is that your kind of sleep, work and play are all in the same location.
Yeah.
And it's so difficult because all of those things seem to sort of gradually merge into one. You know, like you're sleeping, but then you're like, oh, I could just get my laptop out and do some work. Or you're working, it's just like, oh, I'm tired now, let me just put that aside, have a nap.
Yeah.
And then, you know, and play, just sort of, oh, I should, you kind of going, oh, I don't want to do some work at the moment, let's play. Or and I think it's especially hard kind of at the time when you're writing everything up, just because you feel like you need to work much more of the time than is really sustainable.
Yeah. No,
like whereas previously it's a kind of, I need to go and have dinner, let's go home at the end of the day. You just don't really have that anymore. There's no stop on the day.
Yeah, no, I totally get that. I think I really miss just walking into the department, into the office.
Absolutely.
Nice
it's crazy that you can miss the commute, isn't it?
Yeah, the commute that you do every day that's just up and down to the university. But no,
it's just that mental separation that I think is really, really valuable.
Yeah. But I mean, you did it. So I'd love to give you a high five in real life. Yeah, well done again. And perhaps to end on a really positive note, what was your favourite part of doing your PhD?
Well, I think I think I want to say two things. The first part is just sort of a bit of a throwaway in that I love the travel. It's a very field-based PhD, and I feel very lucky that like I was able to get all of my fieldwork in before any of the problems. So I had quite a few good years of going and visiting volcanoes and testing out these pieces of kit, because there is no way you can do it you have to go to the volcanoes to use these pieces of kit. Like you can't really measure it from afar very easily. I mean, there are satellites, and that's kind of actually what I'm working on now a bit. But that's just so much fun. And then secondly, I think just having a really nice group of people around you that you can talk about science with, who are always interested in and kind of learning a lot whilst you're doing that. I always find it kind of fun having problems to crack with people, and so having people saying, oh, you know, what's going on here, and then you chat a bit, and then either for my research I figure out what's going on, and then for someone else's piece of research you say something completely stupid and they go, oh, wait a sec, you're completely wrong, but that gives me an idea. So I really love that.
Yeah, that's good. Yeah, it's always nice when you're down your own PhD rabbit hole and you can just talk to someone else about it.
Exactly. Yeah.
Definitely. Well, thanks very much, Matt, for coming back and chatting to us.
No problem.
Best of luck.
It's been nice to be back. Thank you for inviting me.
Yeah, wonderful. And next up in this episode, we're chatting to Ben Esse. Hello, Ben. And Tom's just had to dip out, so joined by the usual co-host, John Pernay-Fisher there.
Hello.
So thanks for joining us again, Ben. So I think we spoke to you all the way back in October 2019. So it's been quite a while. Well, before we begin, where are you joining us from today? That lovely background image.
I would love to say that I'm joining you from Stromberley, but unfortunately I'm joining you from my flat in Manchester, which is significantly less pretty and has significantly worse food. No, wait, no, I can't say that. The food's lovely.
Yeah, so when we last spoke to you, you were telling us all about your PhD research looking at monitoring ash and different volcanic gases at loads of different volcanoes in Italy and across the world. So yeah, in a nutshell, what was your PhD research about?
Okay, so basically my PhD research was how we can use ultraviolet spectroscopy, which is just using basically the UV rays that come from the sun to try and measure volcanic gas and ash. The whole point of this is that these UV spectrometers are widely used across volcanoes around the world to measure the sort of flux or the amount of SO2 that's coming out of volcanoes to help monitor them. And the beginning of the project was basically, well, can we use all these instruments to also measure the volcanic ash? Because it's really important for things like aviation. Obviously, volcanic ash poses a big risk to airplanes. So yeah, it was trying to use the existing instrumentation to develop new tools to help us detect and then track the volcanic ash to reduce those risks. But then alongside of that, I also spent a bit of time trying to develop new tools to improve our existing gas measurements. So there's a little dabbling in a little both.
So yeah, we mentioned sulfur dioxide there. So I think you were looking at a different mix of gases, but sulfur dioxide seems to come up quite a lot. Why that gas in particular? Yeah,
so it's the main gas that we tend to measure from volcanoes for a couple of reasons. Basically, it's the third most abundant gas that volcanoes generally give off, the first being water vapor and the second being carbon dioxide. But the problem with those two is that there's a lot of them already in the atmosphere. So it's trying to search for a small signal with a large background of atmospheric gas noise getting in the way. Sulfur dioxide isn't quite as abundant, but it's still the third most abundant, typically volcanic gas. So we tend to use that because it's basically non-existent in the background atmosphere. So it makes it a lot easier to detect. On top of that, it's also got nice absorption bands in the infrared and in the UV, which is the ones that we use. Just on the edge of where ozone's absorbing, so we could just sneak in our measurements. But it can get difficult. We could do without the ozone layer. That would make my life a lot easier.
We'll start dumping some fridges, then that'll be fine.
I was all for the CPC, CFC.
So yeah, I believe you've gotten to do a lot of amazing field work during your PhD, and you've been looking at a lot of on the ground measurements. So how on earth do you measure invisible things like volcanic gases and really tiny things like ash? Yeah, so we when we visit volcanoes, where we have these little miniature spectrometers. I don't have one with me, unfortunately, but they're about the size of a wallet, so about this big.
Oh wow!
And we carry them around, and they're connected to a telescope that we can point in a direction. And what that does is it measures sunlight that's been scattered around in the atmosphere. So if you look up at the sky, well, not today here in Manchester, it's very grey. If you are lucky to be somewhere sunny, you can look outside and see the blue sky. Now the sky is blue because the blue light end of the spectrum scatters more than the red light. So the sun appears red because that light goes straight through, and the blue light gets scattered all around the sky and then eventually makes it to us. And it's that sort of, well, blue and then into the ultraviolet that we're measuring. So as that light passes through the plume, it gets absorbed or scattered depending on the gases and the aerosols like volcanic ash that are there. And by measuring how it's absorbed or how it's scattered, that we can get an idea into what gases and if ash is there.
Yeah. So is it very dependent on, say, the weather when you're making these measurements?
Yeah, it is. Yeah, there's a reason we tend to go to sunny places like Italy or the Caribbean. It's a lot easier to make measurements there when you get pretty good weather. It gets a lot more difficult when there's cloud. And one of the really annoying things about volcanoes is that they are mountains and they tend to affect the weather. So often the times it can be lovely and sunny everywhere else, but there'll be a great stonking cloud sat on top of the volcano that we're trying to measure, and that makes it very difficult because all that light just basically gets muddled up and murked up inside the cloud. So it gets a lot more tricky to make good measurements then.
Is the wind quite challenging as well? Have you got to sort of position yourself to be sort of head on against the wind, or does that not really make much difference?
You do have to position yourself with the wind. So basically what I'm trying to think of how we can do this. If I can use, I've got to pour water all over myself. If this is like if this is your volcano here, and then as the gas is sort of floating out sideways, so this is our plume. Basically, you want to try and measure like a slice through that plume,
Okay.
like a cross section, and then you times that by the speed that it's going that way, and that gives you a measure of how much is coming out. So you do have to try and position yourself so that you can get that slice. So sometimes if you're on this side and the plume's going that way, you're like, darn, I can't get there. And it can be quite tricky on a volcano to get around, especially if there isn't good local infrastructure like roads, or if you're on an island like Stromboli, sometimes you have to get on a boat, or if you're very lucky, you get to fly a helicopter.
Yeah, that's cool.
Yeah. So I guess we've pointed out quite a few bits that are tricky in making all of these measurements. So I guess that leads quite nicely onto your work, trying to think about how you can process this data differently and improve these measurements. So yeah, what were your main things you were tackling with that?
Yeah, so I don't know how much into detail you want me to go into radiative transfer. It probably isn't very interesting for a lot of people, but basically we developed this new technique. So the existing methods, you have to take a measure of a reference spectrum of the background sky to get an idea of what the light looks like without any plume there. And then you compare that to your measurement inside the plume, and by looking at the difference between the two, you can get an idea of or how much of the gas is present. Now that's fine, but sometimes it's kind of tricky, especially if the weather's bad, for example. You can't see the plume, and sometimes it's not condensing, so it doesn't have that like cloudy look. So you can't see it even on a clear day. It can be pretty invisible. So it can be hard to find which bit of the sky is your plume-free background reference spectrum. And so what we developed is a new technique which basically does away with that reference spectrum and allows you to get at the gas data directly, meaning that measurements are a lot easier to do, especially for like volcano observatories or people that if you don't have a lot of time, it can save a lot of time by not having to mess around. Excuse me, not having to mess around finding your clear bit of sky, which can be quite difficult at times.
Yeah. So is this something that might be adopted at, say, different volcano observatories in future, or is it, just being tested at the moment?
No, so it's currently actually it's being used by a couple now, which is quite exciting for me. It's always nice to see my software out there being used. The Montserrat Volcano Observatory, which measures the gases coming up from Soufrière Hills volcano on the island of Montserrat in the Caribbean, are using this as their go-to method for flux analysis. And I also recently learned that in Japan, I think it's Sakurajima volcano is being measured by an array of spectrometers using this method as well. So it's very cool.
Yeah, that's amazing. That must be a great feeling to have that something you've done is tangibly being used. I guess a lot of us, our PhDs, just sit on a shelf and no one ever reads them. But this is has actual applications in the real world. It's fantastic. Yeah,
it was a really nice feeling, and it really makes you feel like you're making a difference. That people are actually doing it. It's a nice tangible. Not that all research is very important, obviously, but it is nice to have that sort of immediate gratification.
Yeah, absolutely.
So I believe that you've written up all this really cool work into a couple of papers during your PhD, which we will link in the episode description. But yeah, how has it been writing up papers and writing up your thesis over the past year during lockdown?
Yeah, it was tricky. Especially, we were quite lucky that we moved flat in the middle of one of the lockdowns to a slightly bigger flat. But before both me and my partner were both finishing our PhDs on one little desk in our living room. Having to move the table out of the way every time we wanted to then sit on the sofa, sort of thing. And that blurring of the work and personal life was really tricky. You found that you were working till late in the evenings, and then you stop and you just then move from the desk to the sofa that was just behind you, and and that was quite tough. And I think both of us finishing at the same time as well was quite difficult because we were both very busy and very stressed. And luckily, our hand-in dates were offset by a few months, so she was before me, so I helped her on the day of her hand-in, and then she did the same to me although interestingly, she had her viva on the day that I handed in my thesis. So it was a bit of a day. Yeah,
that's a lot going on in like a small space.
Yeah, her viva was in the morning, and I was sat in in the kitchen, sort of trying to work on my thesis and not really getting very much done because I was sort of sat there fretting. And then she finished, and luckily she passed. So that was really good news. And then, bless her, she sat down and proofread a couple of chapters of my thesis, trying not to fall asleep on the sofa. I don't know how she did it. I was over the moon. But.
Yeah.
So Ben, so I guess just before we say goodbye, then one final question for you. Then, what were the sort of more enjoyable elements of your PhD? Then,
I mean, I enjoyed a lot. Like all the friends we made through the whole degree process has been great. And, you know, you guys and all the volcanology group and the wider sort of PhD students at Manchester beyond was really incredible. But I think personally for me, a big part of my PhD was the field work. I was very lucky to be able to travel to you know, amazing places like here, like Stromboli and the Caribbean and stuff. And that for me, I think was one of the highlights. You know, getting to travel the world and see these amazing places and get paid to do it.
Yeah, well, yeah, that's the thing. Yeah.
And so I think, yeah, for me, that's probably one of the main highlights.
Yeah. But yeah, thanks very much for joining us again, Ben.
Thanks for having me again.
Yeah, and good luck with your research. I believe you're sticking around in Manchester for a few more months, which is great.
Yeah, switching the ground-based measurements for satellite-based measurements now. It's a bit easier to do in lockdown.
Yeah, good idea. But yeah, thanks very much, Ben. See you around.
Thank you.
See you
Bye.
soon.
So our third and final guest joining us for this PhD hand-in thesis special is the wonderful Sam Bell.
Hello.
Hello, Sam. Thank you for joining us. How are you doing?
I'm doing good. How are you too?
Yeah, pretty good. Thank you. So I believe we last had you on the Cosmic Cast about a year and a half ago when you were in the middle of your PhD research. And I believe you handed in about a month ago now.
Yeah, end of January now. Yeah, it's been seems like ages ago.
I know, what is time anymore, eh? But yes, so you were looking at samples of basalt from the Apollo 15 missions. Would you mind giving us a rundown of what your PhD research was about?
Yeah, no problem. So at the Apollo 15 site, they collected all these Mare basalt samples, and then when they were analysed for their bulk chemistries, so take a big bit of rock and see what it's made out of in terms of its elements, they could split them into two groups. So they were slightly different, mainly silica, iron and titanium is what they used to split these two groups. And so the next question was, how do you get a landing site with these two groups of basalts that are there? They've got similar eruption ages, sort of what's going on with the magmas that they were made from. So like there's two trains of thought. One that they were from sort of different sources, so different batches of magma made the two, and they were always two separate chemical batches that erupted and made these samples. And then the other idea was that maybe you had a common source for these two groups, and it was something along the way that they travelled through the crust to be erupted. Some magmatic processes meant that one group was different to the other, and that's how we got the chemical difference at the same site. So I was trying to use petrology, so looking at the minerals, textures and chemistries in the samples to try and figure out, do we have any evidence for one or the other of these two hypotheses of how we got these two sweets. So I looked at crystal size distribution analysis, so tediously drawing around all the crystals in the sample to try and see if there was if we spot any accumulation, so if there's larger crystals in there that we wouldn't have expected from a normal distribution of crystals, or equally, is there some crystals missing from that distribution that might suggest there was some magmatic processes happening. And then also looked at diffusion modelling. So that's taking zoned crystals. So if crystal grows a certain composition, say for a core of the crystal in the middle, and then the magmatic environment changes slightly, you might grow a rim of a different composition, and the crystal is not going to be happy with that. It's going to want to make a uniform single composition, and it'll diffuse across the boundary all the elements that are in the core and the rim. And so we know how quick these things diffuse in certain minerals and certain elements in certain minerals, so we can sort of work backwards and see how long that crystal was diffusing for, and that can tell us about magmatic processes that the crystal's seen and preserved in it. So yeah, that was.
Yeah, so I mean, it's definitely a very tricky thing to study. I mean, even trying to understand magma systems on Earth is really tricky, let alone one that's millions of kilometers away. Don't quote me on that value. However many kilometers away. Yeah, so you were saying you were looking at the crystal sizes. So I guess for a bit of context, what bearing does that have on, say, the processes that would be happening as the magma's ascending?
So yeah, if you've got sort of a normal distribution of crystals, that would suggest that you've sort of cooled it in a closed system, so nothing's coming in and out. You've just melted something, let it cool, crystals are formed, and you get like a normal distribution of what you would expect with the size range of the crystal, obviously bearing in mind the type of the rock, so the grain size of a general basalt. So what we look for is if you've got, say, you could even have evidence of two batches of magmas mixing. So if you've got two distributions of crystals, you can get we plot them as crystal size distributions. So you can get a kink in your graph that say we've got one crystal population and another crystal population. You can also get two-stage cooling, and that'll give you similar shapes where you've got like really fast growing crystals and then slower, bigger growing crystals. So there's lots of different subtleties to what to the naked eye might look like. Just we're not talking about necessarily obviously looking at a rock and being like, oh, there's tons of big crystals there and tons of small crystals there, it must be two-stage cooling. Sometimes it can be more subtleties than that, or it can be the absence of certain size fractions that can indicate different processes as well.
So yeah, it's a lot of work to do, isn't it, to work all these measurements out, I guess. So I know one of the things that you were working on was using something called Chem Scan, which I believe you published a paper on, which we'll link in the episode description. But yeah, what is Chem Scan?
So Chem Scan's sort of like it came about as a way to try and ease the load on anybody doing crystal size distributions and having to manually draw around. I think I did nearly 30,000 crystals or some crazy number like that. So Chem Scan is something that works alongside with a scanning electron microscope. So it essentially produces a mineral map. So whereas when you go on the SEM, you might just get an element map, so you can infer from it, oh, if this particular crystal's got X, Y, Z elements, it must be this mineral. What Chem Scan does is it'll do that for you, and it'll just produce maps of, here's some plagioclase, here's some olivine, here's some pyroxene, and that's based on a list of element definitions that it's got. So we spent a lot of time tweaking the existing definitions to suit lunar samples in particular. Let the Chem Scan run on the samples, and then there's certain processes in the software that will separate minerals out. So you can say, just show me the olivines, just show me the plagioclase, show me the pyroxenes, and then a step further from that, it'll then try and separate touching crystals. So essentially it does what takes me like weeks to do for one sample. The idea would be it would be able to do it a bit quicker, but as with everything, it didn't turn out 100% foolproof, because obviously it was an algorithm that's trying to do something that is, there's certain subtleties to it that humans are just better off picking boundaries between different grains out. So but yeah, it was definitely worth a try, and definitely some samples it's more suited for depending on their crystal shapes than others. So yeah, it was an interesting part of the project.
Then how are things going with the diffusion modeling side of the project then?
Diffusion modeling went well. Yeah, it was quite interesting. Not something that I'd done before, and we managed to get some good time scales, and we sort of looked at the timescales in terms of lava flow thicknesses as well, because Apollo 15 landed close to a rill. So this is like a collapsed lava tube, and then essentially like what we would think of like a river on Earth if you saw like banks of a river, but obviously no rivers up. Yeah.
Just like the one over there.
Yeah.
Yeah.
And then, so like within the walls of the rill, the astronauts could see layers. So we had some sort of rough estimate of lava flow thicknesses, and with the diffusion modeling and the timescales we got from our results, they're sort of within the range of the thick. If we turn that into a lava flow thickness, they're within the range of what the astronauts imaged. So that was quite a nice test. It's maybe a reasonable timescales that we got out of it.
Yeah, that's really cool. I mean, it's not often you get to actually ground truth stuff for planetary science, or you're usually ground truthing it for somewhere else on say the moon. But that's cool that you had that information from that site.
Yeah, it was a nice added extra that it was very handy to have.
Yeah.
So I guess you were quite fortunate, I suppose, that you managed to, but you collected most of your data, I suppose, before lockdown started. So how have you found writing up and finishing your PhD over the past year working from home?
Yeah, it was, to be honest, I was super lucky because I just had like my mum and dad spoiling me rotten and fetching me food and drinks, and I didn't have to worry about anything other than just doing my PhD and writing up. So it was, it worked out very well for me. I can't complain, and especially as you say with having the data and stuff there. I think I maybe did a few crystal size distributions right at the beginning, but again that was using data that I could just do from home and all from there. So yeah, it was one of them situations where you'd say to people, oh, like I wish I could just, like, there was nothing else to do, I just had time to write, like that'd be the ideal situation, and then it happened, and then so I can't really complain.
Amazing. Well, congratulations again, Sam, for handing in. And I guess a nice question to end on would be, what were your favourite parts of your PhD overall?
I think one of the best parts was towards the end, when like everything started coming together and you could actually see like a genuine like thesis of different parts, but they were all sort of linking together, and it sort of, because I guess as you're going through it can sometimes seem like you're doing this bit, but then you're like, oh, how does that relate to like everything else I'm doing, and it can feel a bit disjointed at times, and then it sort of all started to come together, and it was quite nice, like, oh yeah, I have done this, this is half decent maybe.
Okay, that's really good to hear, because as someone who's in their third year and is wondering how it's ever going to come together,
it does.
It does? Okay.
It's up on you, and then you're like, oh, okay.
Okay, all right. I look forward to that moment. Yeah. Oh, that's great. Well, best of luck with the rest of your research, Sam. I believe you're sticking around in Manchester for a few months on a slightly different research project. So yeah, I hope that goes well, and thank you for joining us again.
Thank you for having me.
Thank you.
See you soon. Well, there we go. I hope you've enjoyed this week's PhD hand-in extravaganza. But we'll be back next week for some more Earth and Solar System content. But in the meantime, if you fancy keeping up to date with what we're doing, we're on all the social medias, from the Twitters to the Facebooks to the Instagrams. All the links will be available all the time in the episode description and on the screen below right now. But until next week, see you very soon. Bye.
Bye.